All right. So, section 3.2, derivatives of exponential and logarithmic functions. This will be the last video that I make for the semester. Mrs. Boardman will take over for the remaining videos. You're in good hands. She's won TA of the year many times. So, yeah. All right, let's get started. So let's talk about what we learned last video, because it's very much related to what we're going to learn today. So we talked about how if we have a constant function, then the derivative is 0. If we have a linear function, then the derivative is the slope. If we have x to some power, then the derivative is that power times x to 1 less of that power. If we have a sum of two functions, then the derivative will be the sum of the derivatives. And if we have a constant multiple of a function, then the derivative will be a constant multiple of the derivative. Okay, so let's just remember how that went. So for example, if we have the revenue function, r of q, and let's say the formula is given by 3q squared minus 5q plus 3, I'm going to give you two ways to think about this. So you could just apply this rule. So you could apply really several combinations of the first three rules, and I guess you'll need all these rules really. But these last two rules are kind of so intuitive that you don't really even notice that you're using them sometimes. So for example, if you find the derivative of each piece, then you just add those up, and you don't really think too much about if f of x equals g of x plus h of x, then, and so forth. You just kind of do it. Same with the constant multiple rule. And I think you'll know what I'm talking about after you do these problems for a bit. All right, but there's a few combinations of ways that we could use these first three rules. And just for consistency's sake, it might help during our review to talk about that for just a moment. So we could write this function in a way that we could only use this first, that we only need this first, this third rule here. So 3q squared, I'm just going to carry that down. Just going to rewrite the function. 5q, I could write that as 5q to the first power. And 3, just the number 3, I could write that as 3 times q to the 0th power. Because anything to the 0th power is just 1, and 1 times the anything is the anything. So what I've done is written it in a way that I can directly apply this rule 3 times. All right, so let's do that. So the exponent comes out in front and multiplies by that constant. So I have 2 times 3 is 6, and I have q to the 1 less. I take 1 off the power, so now we have to the first power. That 1 comes out in front, multiplies by the 5, so that's just still negative 5 out there. And then I take 1 off, so I have 0, the power of 0 now. And this 3q to the 0, I could think of bringing out the 0 out in front. So 0 times 3 is 0. And 0 times anything is 0. So I just have 0 here. I don't need to write like q to the minus 1. 0 times it will be 0. Okay. And then I could simplify it to be leaving off the exponents, just like this. All right. So that's how, so we introduced these 3 different rules, but really these first 2 rules are special cases of the third rule. This third rule really takes care of both those cases. All right, so that's that. Now we have some, I just want to simplify the way we're writing things a bit, because it can be written a little neater. So these are the rules that we had written down on the previous page, but you'll see a lot of times that we write d dx or d by dx to mean we're taking the derivative of something. All right, so instead of writing this full sentence here, I can just write the derivative of a constant function. This is how this reads, d by dx of c. That means the derivative of a constant is 0. The derivative of a linear function is the slope. The derivative of x to the a is ax to the a minus 1. The derivative of g plus h is g prime plus h prime. The derivative of c times g is c times g prime. All right, so that's how we'll write our rules from now. So try to get used to that. All right, now we have our rules for this section. We have the exponential and logarithmic rules. They're actually very easy to use. How they got these formulas, that's not as easy to explain, so we won't worry about that so much, but using them is pretty easy. All right, so we just need to practice. So the derivative of e to the x is just e to the x. This is the only case that I know of besides 0 where the derivative of a function is the function itself. In other words, the rate at which the function is changing can be gotten by just the function values themselves. All right, so that's kind of interesting. Very unique function. All right. Now, usually we have this case here because we're talking about the balance in some account, and that's with interest accumulating continuously. So we usually have like some interest rate k, like 5% or something like that. So the derivative of e to the k times x, that k will just come out in front. Not exactly the same as the power rule that we talked about before, but it's similar. All right. Now e is it's a specific number, but in general, whenever you have an exponential function where you have some growth factor or whatever, maybe it's like 1.06 or whatever. The way you take the derivative of that function is you again copy down that function, but you multiply by a factor of ln of that number. Right? So the derivative of a to the x is ln of a times a to the x. And then another very easy rule is that the derivative of ln of x is just 1 over x. All right. So note the difference here, because I do see some students try to, I think, conflate these two rules, and they're very different rules, as you can see. So note the difference between a to the x and x to the a. Here the variable is the exponent, and here the variable is the base, right? And so those have very different derivatives. So make sure you are good at recognizing, is this an exponential function or a power function? Because how you'll work with them could be quite different. Okay, let's look at the derivative of this function here. So 100 times e to the 0.05x plus x squared. So we'll just look at the derivative of each piece. What's the derivative of this here? Well, if I use this rule here, it's of the form e to the kx, where that k is 0.05 in this case. And so we just multiply that out in front. All right, so 0.05 times 100, that's 5. And so we just have 5 e to the x. And the derivative of x squared, that's just 2x, the first power. So our derivative, we just add those two things up, since we were adding the two functions originally, and we get 5 e to the x plus 2x. Okay, so that's that. Let's look at another example. Here we have a sum of functions where we have an exponential function where the base is not e, it's 7. So 9 times 7 to the t, that the derivative will be the same thing, except we need an extra factor of ln of the base, ln of 7. All right, so the derivative of this thing here will be this. The derivative of ln of t, well, that's easy. That's just 1 over t. I can use this rule here. Very easy rule to use. And then to take the derivative of the square root of x, we talked about it last time, but just as a reminder, we need to write that in the form of t to some power, and then we'll apply the power rule. So we'll write square root of t as t to the 1/2, and we will multiply that 1/2 out in front, and then subtract 1 from 1/2 to get 1/2 t to the minus 1/2. All right, so we had a function that was a sum of 3 functions, and the derivative was the sum of the 3 derivatives. And you might see it written like, take the derivative, you might see it written like this. So keep in mind, this means the derivative of the function h of t, which we can write as h prime of t. All right. I prefer to use this notation whenever possible, but I definitely need to know how to read stuff like this when it comes up. So there could be times when you need to write things like this. Okay, so that's that. Let's look at another example. So suppose we have 2 to the e to the negative 0.03t plus 1,000. So this would be an example of exponential decay, and I know that because this rate here is negative, this rate here. So it looks like this function here where the k is negative, and so that'll come out in front. So we'll have negative 0.03 times 2, which is negative 0.06. Oh boy, and I made a mistake here. All right, you're going to have to ignore this 3 here. I didn't catch this. This should be negative 0.03. All right, we don't, this is a teachable moment. This is a teachable moment. So whenever we take the derivative of e to something, that something stays exactly the same. So what's written here will always be the same as what should be written here, which isn't. But you know, luckily I'm not being graded right now. All right, I'm grading myself kind of harshly, but okay. So this should be negative 0.06 e to the negative 0.03 t. All right, whatever's on this exponent for exponential functions, it always stays the same. It always stays the same. And then what's the derivative of what's the derivative of 1,000? Well, that's just a constant function, so the derivative is 0. So we could write plus 0 here, but we don't need to write that. It just drops off. All right? Good. And just a couple loose ends here. So you might see some slight variations on Leibniz notation. Leibniz notation being this thing right here, being the dc/dq. Right? This is like the standard notation, and this is Leibniz notation. But you might see Leibniz notation written like this, and it means the same thing. So this reads like the derivative with respect to q of the function c of q. All right. This reads dc/dq, or the derivative of cos with respect to q. You always hear this language with respect to q. It just means that that's the variable that we're changing. Right? We're considering a relative change of variables. Like we're changing q, and we're looking at what happens as we change c. All right, not a deep thing. Just kind of confusing language sometimes. But just so you know, whenever you have like a function y, which is a function of x, you could see the derivative written as dy dx, or the derivative of y with respect to x. Some people say. All right, but it means f prime of x. All means the same thing. If you find yourself getting frustrated that there are so many ways to say the same thing or write the same thing, I would say, welcome to mathematics. Enjoy your stay, where everything looks different but is actually all the exact same. Right. But anyways, that's that. Just so you know, different ways to write the same thing. And okay, that's the same thing. And that's all I have for you. That's it. I don't know why this says 7. Oh, I forgot to hit compile one more time. So, you thought there was more to this video? The video is actually a little shorter. There's just not that much. It's just fun little algebra problems. Isn't that nice? Fun little algebra problems. A lot of people like algebra, like to do these little rules. I do. And yeah, just get some practice with it, see if you can get it straight, and if not, you can always let me know. All right, that'll be it for today. Have a good one. Good luck with your stuff. All right, goodbye.